Okay, now because we have these equivalences, we can use them to rewrite queries. And there are some heuristics that are typically used in, say, a system R optimizer to rewrite these queries without worrying about cost. And the idea with these heuristics is that they're always good. They're always going to result in a plan that's better than not using these heuristics. So we'll just apply them. And that's mostly true for these heuristics we'll talk about, but not always. And so you can think about for these heuristics when they might not be true. The first heuristic that we're going to apply is selection, cascade, and pushdown. We're always going to try to do our selections as soon as we have the relevant columns to evaluate them. So as an example, look at this query where we're projecting to sname of a selection on boat ID equals 100 and rating greater than 5 with the join of reserves and sailors on SID. Now those selections, boat ID equals 100 and rating equals 5, can be evaluated when we scan reserves for boat ID equals 100 and when we scan sailors for rating greater than 5. And so we can actually cascade those into two selections, one on boat ID, one on rating, and then we can push those selections or commute those selections into the joins on the individual sides. Okay, so applying these selections as soon as we can will lower the size of the inputs to the joins and make the joins cheaper. So the basic heuristic here is that we're assuming that selection is cheap or even free and join is expensive. And so we should always do selection before join. Projections are also good to cascade and push down in most cases. The way to think about it is at any given time in our data flow of tuples through a query tree, we want to have only those columns that are relevant downstream, that are referenced in a predicate or in an output. And so let's look at this example. We're going to project in the end to just sname. And so the question is, what do we need all the other columns for? Well, we'll need them to do joins and selections and things. And so let's try to throw away any columns as soon as we don't need them anymore. So the second version of the query down below has done some cascading and pushdown. And you can see that after we do the selection on reserves of boat equals 100, all we care about remaining is the SID for the join. So we'll push a projection to just SID of reserves on right above that selection. On the right-hand side of the join, all we're going to need is sname for the output and SID for the join predicate. So we can project to just those two columns after we've done the selection on sailors. Okay, so in those cases, at every stage, at every operator here, we're only keeping the columns that we need for downstream operators. And this is useful because it makes sure that, tables that we might input into, say, a sort merge join or a hash table will only have the columns that are necessary, which means they'll only take up memory for the columns we care about. So another common heuristic that is explicitly listed in the Sellinger paper for System R is to quote-unquote avoid Cartesian products. If you have a choice between two query plans that produce the same sub-results, so here we have the join of R, S, and T. If one of them has theta joins all the way through and one of them has cross products, pick the one with theta joins. Always avoid cross products if you possibly can. So this heuristic is pretty good most of the time, but it's not actually always optimal. There are cases, for example, we have two small tables and their cross product is also small. It can sometimes be good to do that cross product rather than joining one of the tables with a big table and then taking the even bigger output and joining it with the third table. So sometimes when you have very small tables, cross products can be good. But as a heuristic and in our discussion of the Sellinger algorithm, we're going to avoid Cartesian products. So you should be aware that not always a good solution, but it's a heuristic that's used to keep our plan space smaller.